Hi, good morning. The lesson today is 4D, length of daylight. It's the connections to sinusoidal functions. All right, so let's talk about good things. Had a tennis tournament yesterday, so I wasn't here, so I'm going to do this while I'm in my third period class. If you hear students in the background, they know I'm doing this. Some of them are trying to listen to actually learn, but most of them are just waiting for the video to come out. The parent function y equals sine x can be transformed using four parameters. Each parameter describes a certain characteristic of the graph, the sine wave graph. Y equals a sine times the quantity b times the quantity x minus c, quantity closed plus d. All right, so let's look at that. A in this y equals a sine, b, x time minus c, all that, it represents the amplitude of the graph. The amplitude is the vertical distance from the horizontal axis of the graph to the maximum value or to the minimum value of the graph. The amplitude is also equal to half of the difference between the maximum and the minimum value. Because they should be the same, if you divide them in half, it should be right here. Okay, so that's your definition of amplitude. Let me move this up or over here. Let me move my face. I'll just leave it there. It don't matter. Okay. So, B represents the angular frequency of the graph. The angular frequency describes how many crests or troughs of the graph are present within a 360 degree or 2 pi portion of the domain of the graph. The angular frequency is also found by dividing 2 pi by the period, which is the horizontal distance between two consecutive maximum or minimum values. And as you can see, the angular frequency is pointed at right here. It's the distance between two peaks, or what do they call them up here? Crests, apex, troughs. You can do the same thing for troughs and so on. All right, C represents the phase shift, or the horizontal translation of the sine function. A sine function will generally start at 0, 0, and they move up and follow that sinusoidal pattern. D represents the vertical translation of the graph. The line y equals d is the equation of the sinusoidal axis, which is the horizontal line representing the distance that is midway between the crest and troughs of the graph. Okay, if this is your sine function right here, y equals d is the line that splits it in half. You've got half between the trough and the crest. That distance is d. Okay, so that's our vertical translation. The number d that's added on the outside is the amount that it is shifted up from 0 vertically. Okay, let's see. I got phase shift. That's C. I got B, angular frequency. I got A, which is the amplitude. So let's talk about all of them together. If we look at the Houston row on the summary table, we're going to subtract the maximum value of daylight from the minimum value of daylight and divide that difference by 2. How does this value compare to the amplitude of A in the regression function? Okay, so let's look at that. If we subtract 841 or 614 from 841, we're going to divide that by 2. So we looked at that chart. 841 is the maximum, 614 is the minimum, and the middle is 113.5. It's very close to the value that's A, 113.26 in the regression model for Houston. That describes the amplitude. If we divide 2 pi by the number of days in a year, 365, how does this result compare to the angular frequency, or this number right here, B? 2 pi divided by 365 equals approximately 0.017, which rounds to 0.02, is equal to the frequency for all 3 cities. If a period of a sine function is the number of units before the cycle begins to repeat, why would the period of the regression model include a quotient with the number of days in a year? Well, that's simple. A year is 365 days long in all 3 cities. Each year, the cycle of time of sunrise and sunset repeats, so it makes sense that the period of each regression model includes the value 365. All right, how does the value for C, the phase shift, in the factored form of your regression equations compare to the x-coordinate of the first intersection points? So the values for C are very close to the x-coordinates for the first intersection points, because that first intersection point would be where the equinox is. And that's where the daylight and nighttime are the same amount of time. How many minutes are there in 12 hours? And why would the vertical translation D be a number that is close to that value. All right, 12 hours times 60 minutes is 720 minutes. Each city has 12 hours of daylight twice a year. On March 20th, the spring equinox, and actually they also show it on in September 21st, the autumnal or vernal, or I'm sorry, the vernal or autumnal equinox. Maximum values for the amount of daylight vary from these starting points. It makes sense to translate the graph about 720 units upward, which is very close to the value of D in each regression model. Why do the values of B, C, and D remain close to the same for the regression models for all three? And then why did the value of A change for all the models? B, C, and D all include information that is true regardless of where the city is located. A changes as the latitude gets further north. So I'm going to launch you with this quick lesson. I wanted to get through it really quickly. You guys check in the Google Classroom for your Google assignment. Real quick, 4 questions. Do your best. In the meantime, be blessed, be a blessing.